pleasure to be here. And for my presentation, I'll leave it, and anyone is welcome to it. I'll probably write it out as a PDF file, but you're welcome to it in the same, in exactly the same form as I presented. I just ask you that if you use it or refer to it and find any mistakes, please drop me an email and inform me what the mistakes are. So I'll be talking about satellite data and satellite data to study climate. And satellite data since the 1970s have revolutionized our study of climate because they provide imagery of the Earth's surface, of the atmosphere, of the oceans, of the cryosphere in a spatially continuous and time-varying way. So we're able to look at changes over time. Now, inherent in this is calibration and many applications of physics and radiometry, which I'll touch on briefly. So it's always good to have some cartoons, and I'm always amused every time cold weather comes, people say, yeehaw, all this global warming talk is just a bunch of hot air. We certainly had this in 2010 in Washington, D.C. when we were hit with snowstorm after snowstorm in February, and people equate the presence of snow with colder temperatures. And that is clearly not true. And for example, I have some slides which I won't show you on the Chesapeake Bay. The last time the Chesapeake Bay froze completely across was the winter of 1977, of 1976, 1977. And since then, the Chesapeake Bay is not frozen solid. So I have a special presentation on that. Just because it snows a lot doesn't mean it's cold. But there are all kinds of funny cartoons like this. And I have several more in the extra materials here. Here's one that I like about clean coal. Mommy, can we see the clean coal? Aren't you a little old to still believe in that? So there's some great cartoons about things like this. So, but on a more serious note, people always say, we didn't realize that NASA studied climate. Well, NASA uses space for scientific discovery as well as exploration. And Pierce Sellers, one of my best friends and former roommates and now next door neighbor, is giving a talk at 2 o'clock, I think, in the Student Center. So just maybe 200 meters down the street. Anyway, so on the next slide, we see some images from probably the most amazing instrument of our species to date, and that is the Hubble Space Telescope. But the same engineers who build the various instruments on the Hubble, which look away from the Earth, build instruments to look down at the Earth. And so what we do if we're using satellites to study the Earth, we use couplings between electromagnetic radiation at various frequencies or wavelengths and specific physical properties of the Earth. And this enables us then to do things like produce cloud-free image from CWIS data, where we can look at the average chlorophyll density in the oceans, as well as the average photosynthetic potential on land. And so it's data like these in the time domain which enable us to study the Earth in an unprecedented way. These same data provide the means to refine and improve numerical simulation models, then to run backwards in time and forwards in time. So this is just a brief summary of my talk. I'm talking about observations from satellites. I'll show that sea level is rising. All of these are based upon observations while the sun is constant. I'll talk a little bit about greenhouse gases, but I want to stress something which many people are not aware of, and that is the residence time of carbon dioxide in the atmosphere is long. That's a very major point of my talk. And then also stress one planet, one climate, one solution. We're all in this together, and we can't hide. Okay, this is a quote from Confucius, which I like, about that you have to have proper definitions to define things so you can have a logical discourse. And without proper definitions, a logical discourse is impossible. We can look at the Tea Party right now and see that. And without logical discourse, nothing can be accomplished. This is why we need observations. Move away from beliefs and let's stress using the scientific method, being empirical, measuring things, drawing conclusions from that. So where do we stand now? Well, the Earth is warming, and we know that because sea level is rising. Sea level is the best indicator of whether the planet is warming or cooling. And sea level is rising. So the first thing we do is we look at the sun and total solar irradiance, which has been measured since the late 1970s, and that has been remarkably constant since these observations started. We can look at ocean temperatures, not from remote sensing, but from the Argo diving buoys, which are revolutionary for understanding temperatures and salinity with depth in the oceans. We can also look at surface thermometers. We can look at atmospheric soundings from satellites. The soundings of temperature and moisture in the atmosphere are fundamental for numerical weather prediction. And they're also extremely important records when you have these through time. We can look at glaciers like the group directly below you is doing with high resolution data, which are revolutionizing our study of the planet. And then I'll also talk about Arctic sea ice, and I'll contrast Arctic sea ice with Antarctic sea ice. So let's look at radar altimetry. So we have radars, the same basic approach which the police use to catch us speeding. You can send a beam down, you know the speed of light. You can make a slight water vapor correction to improve the accuracy, and you can tell the height of the ocean surface to a fraction of a millimeter sometimes. And what we know from these data is that what we're seeing in each of these spikes, this occurs around the December solstice, and so here's one year, here's the next year, so on like this, because the oceans have a temperature flux on an annual basis, and that's what you're seeing here while you have this variation. You fit this with a straight line, and the rise over this record is about 0.3 to 0.4 centimeters per year, or 3 to 4 millimeters per year. Let's extend that in this graph where you can see all the data which have been collected, first from the TOPEX satellite, then from JASON-1, then from JASON-2, and they've been smoothed. And when we look at these data, which started in 1993, we have about this 3 plus or minus 0.4 millimeter per year increase in sea level. And the sea level increase, about 2/3 or just under 2/3 is from thermal expansion of seawater, and about 1/3 is from the melting of ice on land, principally from Antarctica and Greenland, which contain 98% of the ice on the planet on land, and then to a very, very minor extent from other glaciers. So here is an extension of the satellite record on the upper right-hand corner down to about 1870 based on tide gauge stations in various sites around the world. And what you see is there's a lot of variation, so there's a lot of noise associated with these measurements. Part of that is due to post-glacial rebound in some places, but still there's this increase as we see here. But as soon as we get up to this point where we have satellite data, we have much more precise and spatially continuous data. We don't have to rely on a few tens of tide gauge stations. You're probably wondering, what is this and how does this pertain to sea level rise? Well, this is Dennis Stanford, who is an archaeologist at the Smithsonian Institution in Washington, D.C. And all around the Chesapeake Bay, there's been a huge number of Clovis arrow points that have been found. Now, Clovis points are named after the state that I'm from, and that's New Mexico, and Clovis, New Mexico in particular, where these points were first found. These are very old stone tools, and they're beautiful stone tools. So what started this was a trawler, a scallops trawler out of Virginia in the Chesapeake Bay, pulled up about 10 years ago, this mammoth tusk with a Clovis point stuck in it, embedded in it. So the first thing they did was they radiocarbon dated the mammoth tusk. It was 22,000 years ago, plus or minus 500 or 600 years. So at that time, the Chesapeake Bay was the Chesapeake Valley because sea level was about 400 feet lower. Now, the other curious thing is that these points are very similar to similar tools, these points right here. These are very similar to tools that were being made at the same time at the last glacial maximum in Iberia. So hence the name in this book by Dennis Stanford and Bruce Bradley, Across the Atlantic Ice, one of the theories is perhaps these people from Iberia came across to the US East Coast along the edge of the sea ice. It'd be very productive, a lot of marine mammals to hunt. So this is just a slide showing the extent of the last glacial maximum. About 23,000 years ago, here's the Chesapeake Valley then, which is now the Chesapeake Bay. Here's sea level. Florida is maybe 2 or 2.5 times as large then as now. And of course, Minnesota was in the deep freeze. Now, I mentioned that the reconstruction of sea level before the satellite record was based on tide gauges in various places like New York City, Baltimore, Philadelphia, so on and so forth. Here is an example of these data from New York City, and they're discontinuous. They started in about 1850. But now let's look at some data from Stockholm, Sweden. I would expect something similar from Minnesota, and that's post-glacial rebound. If you look at Stockholm, this means sea level is falling. No, it means Stockholm is rising. A massive ice pushed the plates down, and then when the ice was gone, there's what's called post-glacial rebound. The same thing must be happening in Minnesota. Now here is a map showing where Stockholm is. It was under about 2 kilometers of ice, and that displaced the floating plate into the mantle. It's now rebounded. Here is Iberia, so you could walk, or rather France, you could walk from Brittany into southern England. You could invade England across this meadow and tundra. And this is the extent of the ice sheet, the Finno-Scandinavian ice sheet. And then here is the extent of the sea ice, something like this. So the thought is that these people from Iberia, if they had discovered how to use boats, which is highly likely, simply moved along like this. And that's why we have the Clovis points. This is the theory of Dennis Stanford. So this brings us then, let's look at historical sea level rise over thousands of years. Here's the last glacial maximum, and then it's come up like this. We've had a few periods of very steep increase or rise of sea level on the order of just under 2 meters per 100 years. Now the rate of sea level rise is on the order of 30 centimeters per century. So we're way up at the present at 0. And we want to keep sea level at its present level so we don't flood all of our coastal cities. So we know that the Earth is warming because sea level is rising. And when the Earth cools, you have ice in the form of precipitation from the oceans that's stored on land, and sea level falls. And this has a periodicity of about 110,000 years due to the Milankovitch cycles, this coincidence of eccentricity, obliquity, and then the wobble of the Earth. Now let's look at the sun and see if the sun has been constant. So starting in late 1978, early 79, we have data of total solar irradiance, instruments on satellites above the Earth's atmosphere looking at the sun. You have to be above the Earth's atmosphere to make these measurements. Now you'll notice here are 4 different instruments looking at the sun at the same time, and they have 4 different answers. This is called calibration. The scale over here is in watts per square meter. So this is 1365, here's 1370. So over a range of maybe 10 units out of almost 1,400, this is the calibration uncertainty for all these instruments. So, and then this is continued with other instruments. So this continued on through the launch of the SOURCE mission, which had a very well calibrated total solar irradiance instrument, which is called TIM is the acronym for it. And these are those data. And it was discovered that this instrument was very, very accurate. This was some work done by a large group of solar physicists. And so what's happened then is through this intercalibration, they have been able to bring all of these instruments into this among instrument calibration, which is very important. You fit this with a straight line, and you see that the total solar irradiance does not change. So sea level is rising because the Earth is warming and the sun is not responsible. I've heard people from Alaska, like Sarah Palin, say, well, yes, it's getting warmer in Alaska because it's unavoidable there that the climate is changing, but it's due to natural causes, it's due to the sun. Well, based on observations, that simply isn't true. And then, so we're talking about in the satellite record, the total solar irradiance is only varied by 1 part in 500. And this is all associated with the 11-year solar cycle. And this causes a change in temperature on the order of 1/10 of a degree centigrade. But that's variable. It's up, it's down. There's no trend to it. Now, just to make things more current, this is an extension using the source data, which I misspelled here. It's it's SORC, that is correct. And it's extending on through the 18th of August of this year. And once again, you see the very benign nature of changes, or the very constant nature of total solar irradiance through mid-August of this year. Okay, so the Earth is warming because sea level is rising. The sun is not responsible. Let's look first at the ice sheets and see what they're doing. And then let's look at ocean temperature with depth. But first, let's look at the ice sheets. There's a really interesting, actually a revolutionary tandem satellite system called the Gravity Recovery and Climate Experiment. And this studies the gravity field and variations in it very accurately. You have 2 satellites. Here's the first one, here's the second one. They are separated about 220 kilometers in space in exactly the same orbit, and there's very accurate ranging between them from a microwave instrument where you can tell their separation by 1/1000th of a millimeter. So they orbit the Earth like this. So if my left fist and my right fist were the 2 gray satellites, we come upon Molly and we keep going around. We come around again, and the next time the acceleration from Molly towards the first satellite is less because she's lost weight. And that then is measured by the separation between them. And so from how these satellites orbit and accelerate or decelerate, you can back out from the gravitational formula what is the mass which is beneath the satellite. So you can measure mass directly. That's why the satellite is so revolutionary. Now, furthermore, the gravity field is really important, unfortunately, for ballistic missiles. So the gravity field is very well known, because if you fire a ballistic missile from point A to point B and don't know the gravity field, you're going to miss your target. So there's been a lot of work formerly in the classified sphere, but now this has been declassified, about the gravity fields and the geoid and how to measure it. So as these satellites go along, you can look at the ice sheets, Antarctica and also Greenland, as well as the Gulf of Alaska, where you have a lot of glaciers. And you can actually measure how much mass is being lost. You're measuring mass directly. So here we're looking at the Greenland mass change in gigatons. This is all ice, which melts in the summer, and then it snows a lot in the winter, and so it recovers. But there's this downward slope to the mass in Greenland, which from 2003 into 2010 was a loss of about 310 cubic miles of ice. Now there's a hell of a lot of ice in Greenland. And so this by itself would cause a 3.5 millimeter rise in sea level. So you know that the sea level is rising very accurately. You know how much it's rising. Now you're trying to break that down and to reconcile that in terms of how much ice is being lost from Greenland, from Antarctica, and then how much the oceans are expanding due to thermal expansion. Now, when you have data from GRACE over time, this shows where you had your mass losses from February of 2003 through February of 2007. They were concentrated on this part of Greenland. Here's the outline of Greenland. They were concentrated here, but they weren't starting to creep very much up the west coast. But when you extend these data through March of 2011, you'll now see this whole region is losing mass. Now, the spatial scale of the GRACE data is equal to their separation. Each cell of data you have, or each pixel, is about 220 kilometers, because that's the baseline of the measurements. That's the separation of the 2 satellites. can look at Antarctica, and you see the same thing which is happening there, but there is a lot more loss of ice mass from West Antarctica in here, while there is a slight gain from East Antarctica. So you have data like these, which then can be tested by having people go and try and figure out what's happening in these various places to get confidence in the data. This is a summary of the GRACE data from Scott Lutke and Dave Rowland, two of my coworkers. These are the data from Greenland. This is Antarctica, and this is the Gulf of Alaska. And what I think is really cool about the GRACE data is they show the periodicity on the scale of months of the mass variation, increases in mass during the winter, losses in the summer as you come along like this, but all of these lines have a negative slope. All of these three areas are losing mass. So West Antarctica, all around Greenland, as well as the Gulf of Alaska, and you can actually quantify what the mass is. This has revolutionized our study of ice sheets and also groundwater and groundwater depletion in other areas. So we know that the main ice sheets, that 99% of the mass on the planet in ice from Greenland and Antarctica, as well as the Gulf of Alaska, they're all losing mass. Now let's look at thermal expansion of seawater. Water has its maximum density at just slightly less than 4 degrees centigrade, 3.96, 3.97. That's represented by this plot. There's a really incredibly innovative and non-satellite way of getting temperatures and salinity with depth in the oceans, and that is the Argo program. So this is one of the Argo Floats. These are autonomous diving buoys. Here's the scale. They're about 2 meters tall. They have an antenna, and this is the actual mechanism. They're dropped off of boats, and then they dive to 1,000 meters, and then they drift for about 9 days. Then they descend to 2,000 meters, and then they surface. All the time they are recording temperature and salinity every few minutes, and then they transmit these data to a geostationary satellite. They're then beamed down to wherever the Argo data processing center is, and the data are then put out on the web. Now the cool thing is, on the 15th of October, which wasn't that long ago, actually, it was just a few days ago, there were 3,606 floats that were operating. Now these data started, I believe, in 2003, 2004, so it's only recent that we have these data. But for the first time, we're able to get information about the temperatures of the oceans with depth and how this varies, and this is the data coverage. You can't complain about the data coverage. So these data have revolutionized our understanding of ocean temperatures and how that varies with depth. Now, one of the things about the oceans have a huge, huge heat capacity. So from the Argo data, here's a plot. These are 1/100ths of a degree of centigrade. So with the Argo data, which are up here, intercalibration of all the instruments becomes paramount, just like the total solar irradiance. You have to make sure that all of your instruments are very, 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 very well calibrated to exacting standards. Now, these are some of the data from Argo showing the temperature in degrees centigrade over here. So here is the equator. This is at 170 degrees west, going from, it looks like about 60 south to 60 north with depth. So it's data like these which enable us to have a very good understanding of thermal expansion. So we have data from radar altimeters showing sea level rise that has to be reconciled against the gravity data of the ice sheets and the Argo temperature data of the oceans to calculate thermal expansion, and they agree. So once again, we come back to this figure. So we start off with here, with the sea level rise measured by radar altimeters. We then reconcile that by looking at the gravity data for ice mass loss, the water equivalent, and then we incorporate the Argo data for thermal expansion, and we get a number that is very, very, very close to slightly more than 3 millimeters per year. Now, let's talk about graduate students and studying Arctic and Antarctic sea ice. This is one of my favorite figures, because as a graduate student, I was abused in similar ways, although not on a small ice floe like this. One of the things about sea ice is it's really easily measured with passive microwave instruments. And that's because there's a spectral emissivity at a wavelength of 1.5 micrometer of about 0.44, 0.45 of seawater. But for ice, the spectral emissivity, the same wavelength, is 0.8 to about 1, just under 1. So there's a sharp spectral emissivity contrast between them, so you can measure them very, very accurately using passive microwaves. So you're not affected by the absence of sunlight or clouds, as you can measure sea ice and its extent and how it varies. Now, also, one of the reasons sea ice is important is during the Cold War, if you wanted to hide a submarine, and submarines are detected acoustically, you want to be around someplace which is noisy, has a lot of background noise. That's the edge of the sea ice. It's breaking, it's creaking, it's cracking. It's a very noisy place to be. So the various navies of the world were interested where was the edge of the sea ice to either hide or to seek. So this is a picture of 2 British and 1 US submarines which have surfaced at the North Pole. So from passive microwave instruments starting in the very late 1970s, this is a plot of the Arctic sea ice minimum through this year, this big red dot right here, and it shows this downward trend with a lot of variations. Now, the climate change deniers have seized upon this point as saying the Arctic sea ice has recovered. Well, I'd be willing to bet substantially you won't be able to say that next year. It'll be down like this because this seems to be the pattern. Anyway, when you have data like this or like these, they show behavior in an intercalibrated way over several years. And so one of the things about the Arctic is the Arctic Ocean is surrounded by continents. In the Arctic Ocean, you have feedbacks which can operate. So if you have a period where you have very warm conditions, then you don't lose all that warmth to the ocean because the ocean is constrained over most of the margin around the Arctic Ocean. Now, if you look at the Antarctic sea ice, you'll notice there's a lot of variation. There's a slight increase in the Antarctic sea ice, but quite a bit of variation. And this is seized upon by various climate change deniers to say, well, if you take the Arctic and Antarctic and add them together, it's a wash. One is decreasing, the other is increasing. Well, you can't make that comparison because there's no feedback mechanism which operates in the Antarctic. Because the Antarctic is surrounded by oceans. All the heat goes into the oceans. It's not constrained by continents around 2/3 of its periphery. So that's a bogus argument. Now, there's also been, there was a much ballyhooed independent comparison of the surface temperature records by the University of California. And it had been alleged that the 3 groups who have been active in assimilating and comparing surface temperature records from meteorological stations, that would be NASA GISS, Jim Hansen's group in New York City, the Hadley Climate Research Unit at the University of East Anglia, and also NOAA's National Climatic Data Center. They were all fudging the data and doing incorrect statistical approaches in analyzing the data. And so a group funded in part by the Koch brothers at UC Berkeley reanalyzed all of the surface temperature data. They reached exactly the same conclusion. Someone said, this is a great study. They found the sun rises in the east. So this is a comparison now of these 4 data sets, and they are virtually indistinguishable over most of the record. So this is no longer cited by climate change deniers as a source of misinformation on the part of people like me. Now we can also look at temperatures in the atmosphere, which are obtained by microwave sounding, by microwave emissions from different levels of the atmosphere, because atmospheric temperatures can be very important. When you look at the stratosphere, so here we're looking, say, from 10 or 12 kilometers to probably 15 or 20 kilometers elevation in the atmosphere. you'll notice over time that the temperatures are dropping. And so this is a fitted straight line for those. While you'll note at the surface, in the lower part of the troposphere, very close to the surface, temperatures are increasing, and this red line is the slope over time from the surface temperature data from meteorological stations. So how is it the surface is, in the atmosphere close to the surface, it's warming, but it's cooling in the upper atmosphere? The reason is the greenhouse gas blanket of insulation. So the outgoing long-wave radiation is absorbed close to the Earth's surface, and that doesn't reach the stratosphere now. And so therefore the stratosphere is cooling. So as the surface warms, it's getting cooler in the stratosphere. Now, we know from the pioneering work of Dave Keeling about atmospheric carbon dioxide and how this is varied. So here's a picture of Dave Keeling when he was a postdoctoral student of Roger Revell's at the Scripps Institute of Oceanography and established his pioneering measurement station on top of the Mauna Loa volcano in Hawaii. And Dave told me once that when he started making these measurements, when he saw these variations, because the atmospheric carbon dioxide at Mauna Loa increases during the winter until March or April, and then it decreases as photosynthesis starts in the northern hemisphere and plants absorb carbon dioxide down to a minimum in probably September, and then it increases again. When he saw this precipitous decline or decrease, he thought he was making measurement errors. But he kept the measurements going because he was a very compulsive person. And then he saw the same behavior over 2 years, and then he said, this is photosynthesis. We have a measure of photosynthesis in the northern hemisphere on land, and this is an expression of that. So these measurements have been continued. This is one of the iconic records of climate. Now, I published a few papers with Dave Keeling, and he was great to work with, but he was the most compulsive person on a paper. He would fight, he would work hard, he would rewrite, he would do whatever he had to do to be the third author instead of the fourth author. But he was compulsively thorough, and this is why his data are so good. He was a very serious scientist, and he took a tremendous degree of pride, understandably, in what he did. So now we're looking at the Keeling record here in terms of atmospheric carbon dioxide coming along. The Industrial Revolution starts. It starts to increase. It comes along. Then it passes 300 parts per million. Now I should extend this. We're up to 400 parts per million. So that brings me to this cartoon. Of course, honey, human activity has no effect on the atmosphere. Her husband is about to put some more tires in the fireplace to warm the house. We know that we do have an action. We know we are taking actions which affect the composition of the atmosphere, and the increase in carbon dioxide is only one example of that. Now, this is one of the main takeaway points I want to make, because people don't realize what the resonance time of carbon dioxide is in the atmosphere. So when I drove my car to the airport yesterday, I put carbon dioxide in the atmosphere from the combustion of fossil fuels, and in 100 years, a third of that will still be in the air, and in 1,000 years, a fifth of it will. So some people, several students have told me, I was talking to my dad or mom, and they said, it's usually their dad, all this talk about carbon dioxide warming the Earth is crazy because water vapor is a much stronger greenhouse gas. Well, that's true, but the residence time of water vapor is on the order of days. It rains and snows out. Carbon dioxide is the gift which lingers, or the gas which lingers. 1/3 at 100 years and 1/5 at 1,000 years. This is why we have to minimize our flux of fossil fuels to the atmosphere. Now, there's also what's called global warming's evil twin. This is ocean acidification. Simply, as the atmospheric carbon dioxide concentration increases, independent measurements of the PCO2 in the oceans show almost exactly the same slope over time, and this results in making the oceans more acidic. Now I'll conclude with showing some of my work at higher northern latitudes with several co-workers from the University of Alaska and University of Virginia. If we look at the surface temperature data, and here we're looking from 23.6 north to 90 north, there's this rapid increase. So we're looking up here. And this is because of feedback mechanisms in the far north. So what we've done is we have gone out. It's sort of the royal we, because I haven't done any of the biomass sampling. They've done the hard work. They've gone out in the tundra, and they've sampled the biological mass of vegetation at the end of the growing season. So the further north you go, you have a very short growing season. It's basically July and August. It may be some of June. It may be some of September. But it's a short growing season, and plant growth is constrained by temperature. This is a highly temperature-limited system. This is what it looks like. No trees. You have to pack heat because of polar bears. And so there are a few operational concerns when you work in some place like this. But you go out, and so what my coworkers, this is Skip Walker at the University of Alaska Fairbanks, and you sample a series of 1 by 1 meter plots, and then you bring the vegetation back and you weigh it. And so you have calibration areas, and you try and characterize an area that's maybe 2 kilometers by 2 kilometers. So this is a comparison with MODIS NDVI data for specific years and these exact locations where the biomass data were collected. And so here on the y-axis is the plot phytomass in grams per meter squared. And so these are the points, and these are the MODIS normalized difference vegetation index data. And then here we have the same data for the biomass with data from the so-called advanced very high resolution radiometer. And they show almost exactly the same trend and the same behavior. But because of this, you have an ability then for the tundra, and only for the tundra, to extrapolate your findings here in a pan-tundra sense across the entire tundra vegetation domain. So this, but with the AVHR data, which is a data set of mine, we can extend these measurements back to 1981. Here was the eruption of Mount Pinatubo, which caused a cooling of the global climate system, so things dropped. Then we come up, and here is this comparison between the MODIS data in red and the AVHR data in blue. So when you have different satellite data sets, it's always good to intercompare them, especially because MODIS are the gold standard. So what we find is with both, so then we're able to use the AVHR data because they started in 1981. So we start, and we average the first 2 years, and we average the last 2 years, and this change in the pan-tundra biomass is on the order of between 15 and 16%. That's because it's warmer at higher northern latitudes. This is an independent confirmation of the effect of temperature on the carbon cycle in the tundra vegetation domain. This is just a figure showing the same thing. Now we're actually going from 60 north all the way to the Arctic Ocean. In North America, as well as Eurasia. Here are the data in green from the NOAA series of satellites. In blue are the MODIS data. These are temperature data. So you see this is directly related to temperature. So there's some interesting papers on this, which several of us have published. All this work is out in the published domain. I have 2 more slides. This is just a written summary. So there are unequivocal signs of global warming. I've only touched upon a few of them. Sea level is the paramount and the simplest way of telling whether the planet is cooling or warming. Then you look at the sun and see if the sun is constant. Maybe the sun is diminishing. That would cool the planet. It's increasing. That would warm the planet, but the sun has been constant. Since we had instruments above the Earth's atmosphere to look at the sun, there's a problem when you use proxies to reconstruct anything, in my opinion, because they are indirect many times. Then we looked at the gravity data, and we saw this mass loss from Greenland, Antarctica, and also the tidewater glaciers in Alaska. We looked at Argo data to get some idea what's happening in the oceans, to reconcile the laser altimetry of sea level. Then I showed some 2 figures showing that the upper atmosphere is cooling, the lower atmosphere is warming. That's an unequivocal indicator, smoking gun, that there is something close to the surface absorbing the outgoing long-wave radiation. The poles are warming faster than the equator. We have more extreme weather events. Because with warmer temperatures, we have a more active hydrological cycle. So this is how I view the climate system. We are just cosmically lucky Our planet is the right mass with the right composition, the right distance from a star of a certain type. We've been able to maintain water in the liquid phase for several billion years. Now, a few times it's been frozen to a large extent. Other times it's been warmer. But it's been in the liquid phase several places on the planet. And our climate system can very easily be tweaked one way or the other. Here's this daredevil in New York City on top of some skyscraper. It gives me fear of heights just looking at it. But I'll conclude here. And this was a very good cartoon about ClimateGate. It's called The Lion That Squeaked. I could show more cartoons, but they're actually very funny. So I'll stop there and be happy to answer any questions. Or show more cartoons if you'd like to see more cartoons.
If you guys have any questions.